So one question that we might ask is, suppose that we are looking for a field generated by something, some subset of C. What should we expect to be there? Well, one subset that will always be in the field generated by anything is Q. Q is always there. Another way of saying this proposition is Q is the prime subfield of C. That is, Q is the absolute smallest field inside of C. There is no smaller. So one way in which we could visualize this is on the very left hand or on the very bottom. Let's visualize it as a diagram where you go up in size. At the very bottom we have a big Q there. And at the very top of subfields of C, we have a big C. C is a subfield. And Q is in fact the bottom. That's what this proposition is saying. So Q we can put at the base. It's the base of the diagram by the proposition. That we'll prove here in a second. And then there's all these fields that sit in between Q and C. Namely, there's like R, there's like this Q adjoin root 2, there's like this Q adjoin I that we just looked at, there's like this Q adjoin I root 2, there's maybe some Q adjoin cube root 2s. There's so much that sits inside. And if I were to try to draw all of the fields that sit inside, there would be not that much time. We would need uncountably infinite time to do that. Okay, so it's just some of them. And when one's contained in the other, we draw a line between them. So, for example, I is not a real number, so there's no line from Q adjoin I to C, or to R. There's only one to C. Q adjoin root 2 is a subset of R, but it's also a subset of C, and then I should have a line from Q to C as well. Q adjoin cube root 2 is contained in R, but it's also contained in C, and so on. So a lot of this class is going to be studying these diagrams like this. These are sometimes called subfield lattices. Subfield lattices. We'll draw better ones later. Or Hasse diagrams. But the purpose of this proposition is to say, hey, there's all these fields. The top of the field of this diagram is C. By the fundamental theorem of algebra, if we start with Q and we wanted to add roots, we're only ever going to stay in C. We actually are going to stay in something less than C, but nevertheless, C is we're going to visualize as the top. And the bottom by this proposition is Q. I mean, there's no smaller field than Q. Q is the absolute smallest that you need. Okay, so let's prove it. Let's let K be a subfield of C. Then 1 is in K. So by induction, N is in K for all N and N, right? Because if you have 1, you have 1 plus 1 is 2. If you have 2, you have 1 plus 2 is 3. If you have 3, you have 1 plus 3 is 4, and so on, because 1 is there. So you can inductively build. And you inductively build by N is N minus 1 plus 1. You know that the 1 is in K because it's a field, and by the inductive hypothesis, that's in K, so N is in K. But K is a field, so the additive inverses are there. So negative N is in K for all N. Certainly 0 is in K because it's the additive identity. We know that K has all of the integers. Right? It has all the positive natural numbers, all the negative ones, and 0. All right, but K also has multiplicative inverses of non-zero elements. So 1 over Q is in K for all 0 not equal to Q in Z. Great, so it has all reciprocals, but it's a field, so it's closed under multiplication. And since you have all integers and you have all reciprocals of integers, you have P over Q. Oh, that's a terrible P over Q. So P over Q, which is P times 1 over Q, is in K for all P in Z and 0 not equal to Q in Z. But that's exactly the set of all rational numbers. Okay, so having 1 gives you all natural numbers. Having additive inverses gives you all integers. Having multiplicative inverses and being closed under multiplication gives you all the remaining rational numbers. That's it. So we say here that Q is the prime subfield of C, meaning all subfields of C contain Q always. Q is the absolute smallest you can go. You can go no smaller.